Alright, and welcome back to the second session of C# TDD Fundamentals. Today's video should be substantially shorter. There's a lot less theory I want to go through. There is a little bit of new theory, which we'll cover mainly around boundaries and partitions. But before we get into that, we're going to do a quick review of last session. And I mean quick, I'm not going to go through all the theory again. And then once we've gone through boundaries and partitions, there's some practice, the more interesting side of things, I'd imagine. We got two new kartas. We've got a FizzBuzz karta, which is pretty straightforward, nothing too earth-shattering there. It's generally one of the first kartas we pick up. I do have a bonus section, and I always find that section interesting. It's a great opportunity to generally discuss the concept of a learning test. I believe we touched on that very, very briefly. Probably mentioned a sentence or two last time. And the second karta is called an age calculator karta. Now, this you will most definitely not find just about anywhere on the internet. And if you do, let me know. Not that it's a proprietary or, company secret karta. It's just that there's very few people I know that would have done this karta other than people that have been on my course before. It's a fun karta. It's incredibly simple, but it's amazing to see how, as developers, we tend to overcomplicate problems. There's two known solutions to it. I do have a set of tests. If I can find, I'll send to you guys on Slack too. That you need to make sure pass regardless of your solution. Like, these tests pretty much ensure that you've covered every scenario, because it's very easy to slip through things that look like they're going to work, but they won't. I'm not going to provide a reference video for that. I will definitely provide a reference video for FizzBuzz because it's easy and you can find a million solutions out there. And really the point of today's FizzBuzz cart is around exercising that second green bar pattern, and that specifically being the triangulation pattern. We really kind of hammered on the fake it last time. This time we're moving to the triangulation pattern. And like I said before, they're very similar. One, you just maybe have a little bit more guidance and context and better examples than the other one. So quickly, the review. Why do we need TDD? So remember, TDD is not about writing test after. It's about writing test before we write production code. I understand that it's a process of getting there. We will all eventually get to that stage. So why do we need TDD? Because it helps us root out assumptions in our thinking. It avoids mental overloading or overload, trying to model the entire system at once. It reduces fear, which we know makes us more productive and just, generally writing better code. And it creates a natural rhythm. You may have developed other natural rhythms, but this one I find to be quite useful. It's short feedback, which I think is important to any kind of natural software development rhythm. If I have to wait hours or weeks to get feedback, then it's incredibly hard to solve that problem well. Quickly, just a brief revisit of the gears model. If you got any questions about any of this, please shoot me a message on Slack. I know doing this asynchronously doesn't provide a ton of time to have conversation, and I think sometime this month we'll rectify that. Maybe even the next session I might just stay up a little later and join you guys, and we can just have a little more in-person type of Q&A type session, especially considering you're probably going to have questions about the age calculator. I have very little doubt about that. So remember, the gears model was a way of kind of thinking how to use those green bar patterns with some of the other theory. The idea being that the lower the gear, the fewer tools you have in your toolbox. I think maybe that's a good way of thinking about it. Ultimately, we should be adhering to the principles and practices regardless of what gear we're in. It's just sometimes in the medium and higher gears, we're taking bigger steps. We're using more patterns that allow us to take fewer steps to get there. Obviously, the danger is that in doing that, we're kind of building on some level of assumptions. And the thinking is that as you understand the context, understand the domain, you're working with some more in existing code, some of those things, those assumptions are going to have formalized into the code, and you can safely build a foundation on top of them. And don't forget reverse. If you get stuck, It's a way of going back to a green state and trying a new approach. You know, don't sit there for an hour or even 20 minutes, 10 minutes, trying to figure out what's wrong. You know, the idea here is that unlike maybe we've come to become accustomed to, or maybe we were taught, like I was, you know, formally planning everything out isn't really the right solution. Because once again, you're building on assumptions. This isn't building architecture. This is software architecture, and the best way an architect can operate in this world is to defer as many decisions as possible. And this is one of the underlying principles in TDD. It allows me to kind of focus on the meat of the problem before making big upfront decisions. Not to say planning's bad. Dwight D. Eisenhower, I think, general and president, you know, was a big fan of planning, but he said, you know, basically no plan survives first contact with the enemy. So same thing in software. No plan survives first contact with the customer. Not that they're an enemy or anything, but I think it's a good comparison. You know, we may have lots of these grandiose schemes and try to design all this cool stuff, and then the customer throws what seems like a fairly trivial requirement at us, or a change in requirements, or just some kind of alteration to what we want to go about doing, and the house of cards starts to come down. So planning isn't bad, but just understand that this is a mechanism to kind of adapt and facilitate some of those changes to plans. Cool. Quickly, maybe 10 minutes, maybe less, I want to talk about boundaries and partitions. This is a really important concept in testing, whether you're doing TDD or test after, or really kind of any way of ensuring that in software you solve the problem. There's an idea of boundaries and equivalence partitions, but equivalence partitions was too long, so it's just boundaries and partitions. So an equivalence partition is a group of input values where the expected behavior / logic is the same. So if I give it a series of inputs, it's always going to give me the same output. And we'll look at an example in a moment. I know this is incredibly theoretical otherwise. A boundary is where those two partitions meet. So it's basically where adjacent input values belong to different partitions. So on one side, I get one behavior, and literally the next value up on the other side, or something similar to that, I get a different behavior. It's a way of knowing that, you know, when I transition, there's going to be a change in behavior, so I have to be aware of that information to ensure that I'm accurately exercising the intended logic of the system. So let's actually look at an example here, because it's way too theoretical, even for me when I first started thinking about this and reading about it. I was like, gosh, okay, I guess that kind of makes sense. One of my first exposures to TDD was probably the complete opposite of TDD. It's the idea that, you build out all your equivalence partitions and boundaries ahead of time, and then you just kind of write your test, and you write the code, and you kind of fill those in as you go. And it did not work out very well, even though we had a full-time tester. But one of those war stories about how not to do things. I've definitely taken that to heart and gone forward. So let's start with a simple example. We've got this print function here. It takes an input. It's got just a couple conditionals. It basically can return one of three things: TDD, is, or awesome. So anything less than or equal to 0 is TDD. Anything greater than 0 and less than or equal to 99 is. Otherwise, anything over 100 or greater is awesome. So by identifying the boundaries and the equivalence partitions, we're allowing for a more systematic and comprehensive approach to testing. Just basically, it's a way of ensuring that we've exercised the behavior of the system, and we can, from a reasonable standpoint as a professional, ensure that it does what it's supposed to. So like I said, we've got the three equivalence partitions: TDD, is, and awesome. If we break that down at the bottom here, we see that we've got the equivalence partition, the value. So if I give it -1 or -100 or -1,000,000, it's always going to give me TDD. Then there's a boundary as I transition from 0 to 1 that is. And if I give it anything from 1 to 99, I'm always going to get that same output. And there's a second boundary here between 99 and 100 for awesome. And the same thing, if I give awesome 101 or 1,000,000, it really doesn't matter. I'm going to get the same output. So a set of values, a partition is a set of values that always give me the same behavior. boundaries where those behaviors change. A second example, and this one comes pretty much directly from the kata. I know I'm kind of giving away the solution here. Oh noes. Really the goal here isn't about finding an elegant solution to FizzBuzz. It's pretty easy to Google. It's about getting comfortable with that triangulation green bar pattern. And to get there, you're not going to go to this as your first solution, because this is the obvious implementation. There should be some steps along the way to get there. So basically, we've got 4 boundaries, because it's going to either return FizzBuzz, 4 partitions and 3 boundaries. It's going to return FizzBuzz, or the original input. The rules of the kata basically say if it's divisible by 3 and 5, you get FizzBuzz. If it's divisible by 3, you get Fizz. Divisible by 5, you get Buzz. Otherwise, return the original input. So if we look down at the bottom here, we've got our other boundary, which is basically anything not divisible by 3 or 5. Then we've got Fizz, Buzz, and FizzBuzz. And in my bonus section, which even if you do copy this, will probably give you a little bit of a reason to pause and think, it's about prime numbers and returning whiz in the case of a prime number. Like I said, it's a good example of kind of thinking about how to apply a learning test without taking too big of a step. But we'll get into that in a moment. So really, equivalence partitions and boundaries, you're not always going to have these really guided katas, but, at the end of the day, if you think about your conditionals and kind of how things flow through the code, those are natural seams to start uncovering the boundaries and partitions. Now, a partition is going to be, a boundary is a really important thing to test. So basically, if I were to write tests for this example here, I would write some test for other that takes a value somewhere in the equivalence partition. Doesn't matter what it is. It could be 1. And then I'm going to take another value that's close to the boundary. And generally, boundaries are pretty obvious. So like where, let's say 4. It doesn't really fit. Really, if we go back to the previous example, it's a bit easier. So maybe let's talk about this. So from a testing perspective, how do I know I've got enough tests? Okay, so TDD, I'm going to test -2. Cool. Then I'm going to test something on the boundary. So in this case, less than or equal. I'm going to test 0. I need to test 2 things. I need to test for the equivalence partition, and I need to test for the boundary when I'm testing. So now, for just TDD, I've got 2 tests. Somewhere in the equivalence partition and 1 right next to the boundary. Same thing for is. I'm going to test 1. I'm going to test any value from 2 to 98, because they're always going to give me the same thing. And then I'm going to test 99. So why am I testing 3 tests for is? Well, 1's on the boundary. In this case, 1. 1's in the middle of that equivalence partition, 2 to 98. And then the third one's on the boundary again, the next boundary, which is 99. So anytime a behavior is going to change with an input, we're actually going to alter... Well, not alter, we're going to actually test that to make sure that it's covered. So I only ever need 1 in the middle, and I need 1 for each boundary. Same thing with awesome. So now I'm up to 5 tests. 2 for TDD, 3 for is. Awesome, how many tests are we going to have? 2. I'm going to have 1 for the boundary at 100, and then 1 for any value between 101 and whatever maximum integer value is, because it's an int input. So ultimately, I'm going to end with 2, 3, 5, 6. I'm going to have 7 tests. I will literally have 7 tests to test this function. But in doing so, I will know I've ensured that its behavior is tested. It's going to actually always operate the way it's intended until someone changes it in the future. So coming back to this other example, I would say it's a little bit harder to make sure that you're testing on the boundaries. Because you've got an unsequential sequence of numbers. So in this case, I'd probably just have a test for other. I'd have a test for 3. I'd have a test for 5, and I'd have a test for 3 and 5. It's divisible by 3 and 5. So in this case, the boundaries become a little bit more difficult to recognize. I do know that there's defined equivalence partitions, but sometimes the boundaries are almost irrelevant. I say almost irrelevant because in this particular case, there's really nothing to test on them. It's kind of hard to say, oh yes, I'm going to test when it changes from other to fizz. Well, that's just making sure it's not divisible by 3, which automatically fits into the other partition. So this one is a little different, but I think if you think about kind of a more traditional expectation with regards to boundaries and equivalence partitions, think about the TDD is awesome, not necessarily just the get fizz buzz. All right, that's the end of that particular slideshow. So briefly, I'm just going to go to the manual and talk about the 2 green bar patterns we should have in our toolbox by now. So the first one's the fake it. You're just strictly using just inputs to kind of fuzz out what the implementation would be. Triangulation's very similar, but now we've got a couple examples to work with that are going to allow us to more easily triangulate, kind of like a cell phone tower triangulates your location with 3 of them, to triangulate that more generic implementation, which you'll start to see. So obviously we're still concerned about test naming, we're still worried about naming, the arrange, act, assert sections, all the cycles of TDD, all of that still becomes important. I would say in refactoring, with triangulation, refactoring is probably a little bit more focused because it's a little bit easier. You're not just kind of grasping at straws and hoping. You've generally got an example and you're just trying to figure out how to implement that in the code. But like I said, I'm going to do a quick little video after this one to show you. One more thing I want to cover is the actual kata. So here's the kata, fizz, buzz, whiz. Oh, sorry, fizz, buzz, and fizz, buzz. The whiz comes at the end. So the first portion of the kata, you've got the examples, you've got the expected. It should be really easy to triangulate. My only advice is don't go down the list because it's going to be really hard to triangulate. Group into an equivalence partition, so 1, 2, 4. Then do that implementation. Then go do the fizz, and then the buzz, and then the fizz buzz. Stick to an equivalence partition because this is such a guided kata while you're doing the work. And then when you're done, it's the prime number section about, oh gosh, okay, now I'm going to add a little whiz component. So obviously 1's not a prime number. 2 is, so it's going to return whiz now. Because instead of returning the number, I return whiz. With 3, it's a fizz whiz. With 4, it's 4. With 5, it's a buzz whiz. Obviously, if something was divisible by both 3 and 5 and somehow prime, it would be a fizz buzz whiz. So that's the thinking there. I will demonstrate in the video the idea of a learning test and kind of how to make that big jump. Given that you have a very small number of patterns in your belt. And anyway, a learning test is always great because this is going to replicate using your patterns, getting stuck, needing to kind of take a backup step. Remember, learning test is more something we do in the reverse gear. So really, we're going to be still using low gear, bridging onto the verge of medium gear. We'll definitely go medium gear for the age calculator, and we'll be using reverse gear as well. And then quickly, the age calculator kata, the one I am definitely not going to give you a working start or solution to. And even if I have it on GitHub, I'm probably actually going to erase it. But maybe not. Just please don't look. Really give this your own shot. It seems incredibly simple. The bonus is just something there because I like to put bonuses in my kata. But it's really just around calculating someone's age given the current date and their birthday. Sounds simple. And if you do get to the bonus section, that's cool. Kind of a bit more on the whole triangulation concept, equivalence partitions and boundaries. But this one's a really good one for equivalence partitions and boundaries, a lot less guided. So you may need to do a little thinking or want to do a little thinking, or you may want to just jump right in. Either one's a perfectly acceptable solution. All right, guys, I hope you have fun. I hope this makes sense. If you have any questions, shout out to me on Slack. Otherwise, go team!